An operating system, or OS, is a piece of software that manages other software and hardware on a computer. A real-time operating system, often abbreviated RTOS, is a type of operating system intended to meet hard deadlines. You'll often want to use an operating system when you want to run more than one piece of software on a system at a time. Let's say we're developing an operating system for a phone, like Android or iOS, and let's say a user wants to stream a movie. So we might break down that streaming experience into two functions: downloading chunks of the movie from the internet, which we'll call Job 1, and displaying each chunk to the user, which we'll call Job 2. These jobs can be individual programs or concurrently running pieces in one program, known as threads. Let's also assume that our smartphone here has only one processor core available. As a result, the processor will need to jump between Job 1 and Job 2 fairly quickly to give the user a seamless experience while watching a movie. I've listed a third job here, which is the underlying software in the operating system, whose job is to swap between these programs or threads. This is known as context switching, and it can sometimes be time-consuming, as the operating system needs to save things like the current register states, memory locations, and the program counter. Note that the focus for most general-purpose operating systems, like our phone example here, is on user experience. If Job 1 drops a packet, or Job 2 needs to skip a frame to catch up, things might stutter slightly, but most users shouldn't notice or care too much. Let's see how this differs from a real-time operating system. Modern automobiles are packed with microcontrollers running specialized operating systems to manage functions throughout the vehicle. These microcontrollers are often packaged in a protective case along with other electronics in what's known as an electronic control unit, or ECU. Now, let's say you're working on the ECU that controls the brakes for a new car with automatic emergency braking. Under normal conditions, you might simply be pulling for pressure applied to the brake pedal to assist the driver with the braking system and turning on the taillights. However, let's say you get notification that one of the distance sensors in the car detects an impending crash. A new high-priority job preempts the regular job and begins to automatically apply the brakes. In this situation, time is critical. Frames can't be dropped, or you risk injuring humans. As a result, we need to use a real-time operating system to ensure that strict timing deadlines can be met by our high-priority jobs. Note that we lose some computing time to overhead incurred by the scheduler, which is the piece of the operating system that determines which job should run next. Once the high-priority job is done, the processor can return to running the lower-priority job. We normally see real-time operating systems on microcontrollers, whereas we usually see general-purpose operating systems on microprocessors. We can generalize the type of processor and operating system we might need based on these factors. If you don't need a lot of speed and only need to run one job, a simple 8 or 16-bit microcontroller is often good enough. Because these normally don't run any type of operating system, you'll often see writing code for these referred to as bare metal programming. While you can do bare metal programming for the beefier 32-bit microcontrollers, like our STM32 line, you'll likely run into situations where you want to run multiple jobs at the same time and assign priorities to them. In that case, you'll want a real-time operating system. When you enter into the microprocessor world, user experience is often the priority, as you need to worry about an interface and several layers of memory management, like registers, RAM, and a hard drive. Here, a general-purpose operating system is appropriate, such as Linux, Windows, Mac OS, Android, and iOS. In addition to cars, real-time operating systems can be found in Mars rovers, pacemakers, and lots of IoT devices. If you need to meet critical timing deadlines, want to run multiple tasks, and enjoy having some code portability, an RTOS can help. The idea of running multiple jobs at the same time on one processor core is known as concurrent programming. If you've done concurrent programming before on a computer, you might be familiar with the concept of threads, which are just individual pieces of a program that run independently of each other. In my previous examples, what I call jobs might just be threads in one program. We are going to look at FreeRTOS, which is a very popular open-source real-time operating system. In 2017, Amazon took over the FreeRTOS project and now distributes it under the very permissive MIT license. STM32Cube IDE comes with FreeRTOS bundled in its libraries, which makes using it quite easy. On the left side of the site, you can click FreeRTOS and get a link to its API. Here, we can find the functions we need to create and manage tasks. Tasks are what FreeRTOS calls its jobs, something analogous to threads. The good news is that if we use the CubeMX software to set up FreeRTOS for us, we won't need to worry much about these specific functions. However, this reference is here if you need to know underlying FreeRTOS stuff. For our purposes, we'll want to use the CMSys RTOS library. You might remember this diagram from the first episode, where we talked about using STM32's HAL library. This time, we're going to be using an RTOS. Specifically, we're going to use FreeRTOS as our real-time operating system kernel. With this framework, we'll want to make calls to the CMSys RTOS API, which acts as an abstraction layer to FreeRTOS. CMSys RTOS is maintained by ARM, and we'll be using version 2. On the side, under Reference and CMSys RTOS API v2, you can see the functions we have available to us. We'll mostly be relying on these functions to control FreeRTOS. Notice the terminology difference. CMSys RTOS refers to the individual jobs as threads, whereas FreeRTOS called them tasks. That can help us know if we're dealing with the CMSys RTOS abstraction layer or the underlying FreeRTOS. In STM32Cube IDE, start a new STM32 project. Once again, I'll be using the Nucleo L476RG development board, so I'll give the project a name with something like FreeRTOS Blinky. We'll want to use two different tasks to control the onboard LED, which has already been configured for us on port A pin 5. In the Categories tab, go to Middleware and click on FreeRTOS. Change the interface from Disabled to CMSys RTOS v2. In the configuration pane, we can see that most of the parameters are defined for us. These settings should be good enough for an initial test program. The important thing here is that preemption is enabled. This allows the scheduler to stop tasks from running in order to run another task of higher priority. Go to the Tasks and Queues tab. You can see that we already have one task defined for us. Let's change its name to Blink01 and change the entry function to StartBlink01. An entry function is just a function that gets called in order to start a task or thread. Notice that the priority is set to OS normal priority. This is the default priority. We can assign tasks to be a higher or lower priority than this, but we'll leave this one at default for now. We could have just one task, but that's no different than a single forever loop. So add another task and call it Blink02. Change the entry function to StartBlink02. Click on the priority drop-down list to see the available priorities we can assign to this task. Higher priorities tell the scheduler that this task should take priority. However, we'll set this task to just below normal so that our first task takes priority. Save the file, and we get a warning about changing the time base. SysTick is a special timer in most ARM Cortex-M processors that's usually reserved for calculating time slices in an RTOS. By default, SysTick triggers an interrupt every 1 millisecond. Since we're using a fixed priority RTOS with preemption, tasks with higher priority will be executed first. If several tasks have the same priority, they will be executed in a round-robin type fashion. On each SysTick interrupt, the scheduler will stop the current task to execute the next task with same or higher priority. The problem is that the STM32 HAL API uses the SysTick timer to determine how much time has passed since restart. This is useful for things like the functions HAL_delay and HAL_getTick. HAL requires this timer to be at a very high priority in order to keep somewhat accurate time, at least without a real-time clock. FreeRTOS, on the other hand, requires that the time base for its scheduler is of a much lower priority. One easy fix for this is to use a different timer for HAL and leave SysTick for FreeRTOS. So we go into System Core Sys and find where the STM32 HAL selects the timer for its time base. Timers 6 and 7 are often extremely basic timers with little configuration parameters, so they're best used for basic counting, just like we need for the HAL time base. So I'll go with timer 6. Save again, and CubeMX should generate code without any warnings this time. You can see that a middlewares folder and FreeRTOS files were added to our project. Open up main.c. At the top, you can see that CubeMX automatically declared the two task entry functions for us. In main, you can see that some OS kernel functions were called, which are part of CMSys RTOS. Farther down, you can see how threads are defined. We give each thread a name, priority, and stack size. This struct is then passed into the OS new thread function along with the name of our entry function to that thread, such as startBlink01. Finally, OS kernel start is called, which begins running the scheduler and calls the entry functions to our threads. At this point, the RTOS has control of the system, and we should never exit from this function. As a result, you don't want to write any code past it, including in the while-one loop. Scroll down to find the templates for our thread entry functions. Each thread should have a place to run some setup code and a forever loop. In the forever loop, we're simply going to toggle our LED just like we did in the first episode. For the first thread, I'm going to toggle the LED every 500 milliseconds. Notice that I'm using OS delay here, which is a CMSys RTOS function instead of the usual HAL delay. OS delay allows the scheduler to run other tasks while we wait, whereas HAL delay might not. Ideally, we should never leave this forever loop unless the thread is terminated. However, it's usually a good idea to add a call to OS thread terminate to tell the scheduler to gracefully terminate and clean up this particular thread in case something happens, like you accidentally call break inside the forever loop. Let's repeat this same process in the startBlink02 function. Note that this thread has its own separate forever loop. To us users, it will appear as if the two threads are running at the same time. If there's any question as to which should run first, Blink01 will take priority since we, well, set its priority higher. The difference here is that I'm going to change OS delay to 600 milliseconds. This should create an interesting effect as the two threads compete to toggle the same LED at different times. Once again, we tell the thread to terminate itself gracefully if it ever leaves the forever loop. Let's build the project and start the debugger. Inside the debugger, press the resume button. The LD2 LED on your Nucleo board should begin blinking and changing its duty cycle in distinct steps, thanks to the two threads toggling it at different times. This is just the beginning of running multiple threads on a microcontroller. How to share resources and synchronize these threads through things like queues, mutexes, and semaphores would take an entirely separate video series. But for now, have fun hacking on your STM32 with FreeRTOS, and please subscribe if you'd like to keep up with more videos like this.